Okay, this is a tabletop rocket problem from an MIT review packet on momentum. So what we got here is a rocket that has a total mass of m naught, half of which is fuel, starts at rest on a long table. Coefficient of friction between the rocket and the table is mu, that's both static and kinetic. At time t equals 0, the rocket's ignited, ejecting fuel out at a constant rate of gamma, which is dm dt, with a velocity of vex, the velocity of exhaust gas relative to the rocket. There's a constant gravitational acceleration g downwards. What condition, part A, must be met for the rocket to start moving? Well, you just look at the forces that are on it, right? Draw a little free body diagram. Of course, we got the weight down, a normal force up. We're going to have the force of thrust forward and the friction backwards. So to have any kind of A, the force of that thrust has got to be infinitesimally greater, just greater than the force of friction, right? That's the limiting factor, is the thrust got to be greater than friction for it to start moving. And thrust, so we went over, in my classes anyways, prior, derived the formula for the thrust of a rocket. And we got that thrust is equal to negative vex dm dt, because vex is a vector, force is a vector, so the force is going to be opposite in direction to the exhaust gas. And so the exhaust gas times the burn rate, the rate at which you're using up the fuel, tells you the thrust. Now, assuming the rocket satisfies that requirement, what's the maximum speed that can be achieved by the rocket? So we got to figure out the speed at which, now you got to understand, the rocket's going to keep going faster and faster until it runs out of fuel. So it's going to have that thrust continually accelerating it, and then when it burns out of fuel, there's no more thrust, no more, it's going to start slowing down then because of friction. So that Vmax happens when all the fuel's gone. We've got to know that. Vmax, that's when all the fuel's gone. So when is that? Right? We got m/2 of fuel, and we're burning it at dm dt. So how much time does it take to burn all that is what we've got to know there, right? We're burning at dm dt, so find that time. M naught over 2. That m naught over 2, that mass of the fuel, that's got to equal the rate at which you're burning the fuel times the time that it'll burn, right? Burn it at 5 kilograms per second for 6 seconds, you burn whatever, 30 kilograms. So T, that T therefore is going to be m naught over 2 dt over dm, but we have that dm dt, we call it gamma. So that's going to be divided by gamma. There is the T, because that dm dt is gamma. That's a fixed rate. That's a constant value, too. That's important to know. Constant burn rate, constant exhaust thing. All right, we know that. So let's set up our equation. We've got Newton's laws applied here, that some of the forces applied to that rocket is m times the A of the rocket. Well, we've got the force of thrust pushing it forward minus the friction opposing that motion equals the m times the A. Now that m changes. It's m as a function of t. So what's that thrust? That thrust is this. It's negative. Now the thrust is to the right, but the exhaust glass is to the left. But we got to keep track. This is all vector stuff, so we got to keep track of our vectors. I can put in gamma. I'm going to put in dmdt, and you'll see why later. Minus the friction. That friction is mu n. Now the normal force is going to be equal to the weight here because of the symmetry of the situation. So it's mu mg, but that changes with time, right? And that's going to equal m a. Now a is the ddt, right? We want to find v, so we got to get an equation that gives us a v. So I'm going to change that a to a dv dt. So I've gotten v into my equation. This v is a constant. That's not the one we're looking for. This dm dt, that's a constant. Burn rate. dv dt is not constant. The acceleration is going to change. But we have this, but how are we going to, we've got to like get to just the v, so to get rid of the dv, we got to integrate somehow. But I got that dt down there and a dt here, so I'm going to multiply everything through by dt. And let's see what happens then. So we got a negative vx, so multiply through by dt, that leaves this as dm minus mu m as a function of t. I'm going to put the g in front actually because the g is constant and the mu is constant also. G mass as a function of time times dt equals mass as a function of time times dv. All right, I got these masses, but I got a dm there, right? When we integrate, if we got a dm, we got to put all the m's with a dm, all the t's with dt, all the v's with dv. Luckily, there are no v's, so that's nice. There's no t's, that's nice. But there's these m's. There's these m's. Luckily for us, if we divide everything by m, these guys lose their m, and that gets an m. So we get minus velocity of exhaust gas dm over m minus mu g dt equals dv. All right. So I got three differential things with different, this is a dm, dt, dt. I'm just going to integrate them all, but then all the limits have to match up. So I'm going to integrate this. Vex is a constant. I'm going to integrate this term. Ug is a constant, mu g, and I'm going to integrate that term. Now the limits have to match. So I'm going from zero velocity, because it starts at rest, to v max. I know that v max occurs when all the mass runs out. And the time that occurs, we're going from time 0 to this time up here. This is the time when all the mass runs out, is m naught over 2 lambda, 2 gamma rather. M naught over 2 gamma. Can you read that? There's an m naught over 2 gamma. We can zoom in on this so you can see a little better. And in this, we got to do, you have to do the whole rocket is going from m naught to m naught over 2. You can't do just the fuel. You got to do the whole rocket on that. Because the fuel goes down to 0, and when it hits that 0, you got a little bit of a problem that you've got like infinite acceleration due to that. So your rocket can't be 100% fuel, because at that very end point you've got no mass, so you have infinite acceleration, so it causes a little problem. So you never have a rocket that's 100% fuel. Okay, so now that we have those and we distribute that through, you'll see I had some work here. You got the minus Vx, we integrate that, we got m to the minus 1, that's ln m, and that's going to m over 2, m from mo, minus mu g. The t is going from 0 to m over 2 gamma, and that's going to equal our v, which is going from 0 to v max. All right, so what do we got here? We get a negative Vex. Put those in. We got ln m naught over 2 minus ln m naught. Right? And we'll reconcile all that stuff out later. Let's do this one. This one's pretty easy. Minus UG. So the 0 becomes 0. That becomes, and that's m naught. M naught over 2 gamma equals V max. All right, so we got it. There we're done. We just got to make things look prettier. So over here, we have that negative. We can distribute that through. So that's Vex. And then the difference in the ln's, it's now m naught minus this one, it's now ln over m naught over 2. So 2 up there, that cancels out. So we got ln 2 minus mu g m naught over 2 gamma equals V max. So we can get rid of that m naught there. It's ln 2. This should end up being a positive number. So Vex and ln 2, that's positive. If he had done it the other way, he would have ln a half. He would have negative Vx ln a half, and ln of a half is negative ln of 2. So the negatives would have worked out that way. And coefficient of friction, gravity, initial mass, 2 gamma, the burn rate, that's dmdt, the burn rate, and that equals P max. So there. That's figuring out how fast it goes. Now how far it goes, that is just after the fuel runs out, and just in terms of V max, you don't got to put all that junk in there, just call it V max. That's just the work of friction is going to be the change in kinetic energy. To find that, how far does rock travel in total? That's a little more work, where we got to go back up here and where we get this equation for V, but we need to put it in terms of just Vt, not V max, V at some time, and then we take V, and V is dx dt. We can do a similar process, but it's a little more involved with some U sub and stuff. That's for another day. All right.